Today I will talk about rigid analytic Hyodo-Kato theory. This is joint work with Kazuki Yamada. In my talk, I will tell you about the construction of rigid analytic Hyodo-Kato theory, but also about certain features that we developed with a view towards application. I will start with some motivation. That should make clear where Hyodo-Kato theory came up. Let us start with the classical theorem. So Z should be an algebraic variety over Q, which is projected and smooth. Then we consider it's the Hum homology, or more precisely, it's complex, the Hum homology. Which can be computed by the Hum complex. And also its singular homology. Their set of C denotes the topological space over the complex numbers associated to Z. Then the Hum theorem tells us the following. Namely, that the following pairing between the Hum homology and singular homology given by integrating is non-degenerate. Dually, this means that we have an isomorphism between complex vector spaces. However, as a remark, this is not induced by an isomorphism of Q lattices. Now we are interested in a periodic analog of this. So let be as before, namely a dry variety over Q, which is smooth and projective. Then we can as well consider its different homology over QP this time. And this analog of the singular cohomology, we will consider its periodic Ertl cohomology. These are finite dimensional QP vector spaces, and there is a continuous Galois action. Now the following question arises. Namely, is there a periodic ring, which I call B, which contains all periods of varieties over QP, such that there is an isomorphism between the Dirac homology of that and the Ertl, periodic Ertl homology of that. And secondly, we also want that we can recover both cohomologies from each other. And in particular, we would like to recover the Ertl cohomology from the Dirac cohomology. As a first remark, I would like to point out that B cannot be Cp, which would be the analog of C. However, Fontaine constructed a ring, a period ring called BDR, together with the filtration and the Galois action. contains a formal analog of 2 pi I. And with this ring, now an analog of the Ram, a first analog of the Ram's theorem was possible. This was first a conjecture, which is now a theorem due to Falking. Namely, let that be a proper smooth variety over a finite extension of QP. Then there is the isomorphism. Which I call alpha dr between the Ram homology of that and the Ertl homology tensors, both tensored with DDR. Which is compatible with the Galois action and the filtration. Moreover, if we take the Galois fixed points, we can recover the Ram homology from the Ertl homology. Where Gk is the absolute Galois group of K. However, we cannot go the other way, meaning we cannot recover the Ertl homology from the Ram homology. In order to do this, we need more structure on the left-hand side of this isomorphism. With this additional structure, formulations of several central conjectures of Pierre de Koch's theory became possible. Such as the crystalline conjecture, which is now a theorem due to several persons. So first we have the proof of quantum messing. Then there was a proof by Felting. Kato messing. And meteorites. Another one is the semi-stable conjecture. Which is now a theorem due to Tucci. And Felting. Meteorites. In the rest of the talk, I will now talk about the additional structure on the RAM cohomology. So let me introduce first some notation. We fix a prime P. Capital K should be a finite extension of QP. V should be its ring of integers. M should be its maximal ideal. Small k, the residue field of V. W, the ring of grid vectors of small k. And F, the fraction field of V. We will use log structures. So let me introduce the following shorthands for this. For V, we denote by V sharp the log scheme, which has as underlying scheme the formal scheme of V and the canonical log structure. Then we also have W naught, which has as underlying scheme the formal scheme associated to V, and as log structures the 1 to 0 log structure. Then we have K naught, which is the reduction of W naught mod P. And for any scheme or formal scheme, we denote by X empty the log scheme which has as log structure the trivial log structure. Now we assume a very nice situation, namely in the situation before. We assume that Z is a nice integral model. So a nice and, for example, is semi-stable. And I denote by Y equals X naught, it's special fiber. And by Xk, it's generic fiber. Now we want the following. We want to endow the Hahn homology with the additional structure of a Frobenius morphism. And the monodromy operator. Which satisfies the equation NP equals TPS. To obtain an object which lives in the category of filter Pn modules. And usually this is obtained via a certain comparison map to a richer cohomology theory. And this brings us to the following definition. A Hyodo-Kato theory consists of the following data. A cohomology theory of finite dimensional F-vector spaces. I denote by hk of x. I check the Frobenius linear map called the Frobenius. And you put an operator n which together satisfies the equation nc equals TPS. And lastly, a functorial morphism from the Hyodo-Kato homology to the Dagan homology of the generic fiber, which is an isomorphism of the tensor is with K. With all this data, the Hyodo-Kato theory is the basis of the construction of the so-called symptomic homology, and we achieved this by using a rigid analytic approach and by adapting to this situation a certain construction by Kim and Hein. In the following, I want to explain to you our construction. I will explain the construction of rigid analytic Hyodo-Kato theory locally. So we assume that Y is semi-stable over K. And Z should be a lift to the following block scheme. Which I call S, which is the weak form of scheme given by WS with a log structure that tends 1 to S. And I note in particular that this is log smooth over WMP. Then I denote by X the product with recharge, and by Y I denote the product with W not, and by Z, X, and Y German letters, I denote the associated Decker spaces. Then we consider the following CDGAs. We have the log-Dagan complex of Z over W nothing. We consider W tilde Y to be the complex given by tensoring this one with OY. And we also consider complexes, both of the complexes with additional variables. Denoted by U. Where in both cases, UI are we are trying degree 0 elements, UI. Satisfying the following. dui plus 1 is given by minus d log s times ui, and u0 equals to 1. The multiplication is given by ui times uj equals I plus j factorial divided by I factorial times j factorial, ui plus j. And the Frobenius is given by the Frobenius on the complex, and the Frobenius of I should give me t to the I ui. And similarly, the monodromy is the only linear morphism defined by n of ui equals ui minus 1. With this notation, we can define the rigid analytic Hyodo-Kato here of y. As the cohomology given by on set, on the Dagger space of set, and the complex of set over W nothing and U. Together with the used method of Frobenius and monodromy, which satisfy, of course, the desired equation by definition. To give you a reason why this makes sense, we have the following commutative diagram. So here, instead of just, here consider form power series instead of just polynomials. Here I consider the complex, the lockdown complex of Z over S. And here I basically do the same for y, for this complex tilde. And we have these vertical natural lengths. And here we have the log complex of y over w naught. And this computes the rigid cohomology of y, the U log rigid cohomology. And we could show that we have quasi-isomorphisms here, and here, and here, and here, and here not in general. So maybe I should tell you that here U, I is mapped to 0 in both cases. So we see in particular that this complex that we use to define the rigid analytic Hyodo-Kato theory computes exactly the complex that we want it to compute. Moreover, we have a natural morphism from this Derham complex over X to the Derham complex of X over V sharp. And we use this to define the rigid Hyodo-Kato map. And fourth, for a uniform answer, and Q non-zero in the maximal ideal, we define a morphism denoted by psi pi q. To the Derham cohomology, which is the Derham cohomology of X over V sharp. By the natural map given on the complexes like this. And sending UI to the element minus log Q to the I divided by I factorial. Where log Q is the branch of the p-adic logarithm such that log Q of Q equals 0. This morphism psi pi q satisfies the following property. First, psi pi q is independent of the choice of pi of a uniformizer. More precisely, for two choices of uniformizers. And fixed q, we have the following, that psi pi q equals psi pi prime q. However, psi pi q depends on the choice of a branch of the p-adic logarithm. So for q and q prime, we have the following formula. So in this formula, in particular, the monotomy operator appears. And finally, what we also wanted, of course, is that for any pi and q, this becomes the quasi isomorphism of the tensoring with case. Now I would like to mention some additional features. Based on our research and discussions, Kazuki developed a theory of coefficients for our Hyodo-Kato theory. And this in turn allowed us to construct a theory of compact supports. For this, let Y be a strictly semi-stable log scheme over K0. We denote by NY its log structure. And B should be a horizontal divisor. We can consider a log structure which is associated to this horizontal divisor, and this is a monogenic sublog structure of NY. We call it MB. doubly nothing. And this monogenic sublog structure associated to D and uses also a monogenic sublog structure of the log structure of Z. Then we let OZ and D be the locally free OZ module, which is locally generated by a generator of MD. By doing, you obtain an isocrystal which I denote by OY over W nothing of MDs. So this is an overconvergent isocrystal of Y over W nothing. Then we make the following definition. For any isocrystal, we set E of MD to be the tensor product of E with this isocrystal. And we set R gamma HK. So we define the compactly supported rigid cohomology of Y as the cohomology, the Hyodo-Kato cohomology of this isocrystal. Sorry, I forgot to tell you that we have to assume that Y is positive. And similarly, we can also define compactly supported rigid cohomologies for different base schemes. I just note the most important ones here. Exactly as in the case without compact support, we can construct the Hyodo-Kato map. So we have a map from compact support Hyodo-Kato homology of Y. Depending on the choice of a uniform of a branch of periodic logarithm and not of the choice of a uniformizer. And it fits in the following diagram. This is exactly it in the non-compactly supported case. Where all the triangles commute, except this one and this commute if Q equals pi. Now our theory with compact support has the following properties. First, if the overconvention isocrystal, with we start, is unipotent, then all the compact supported rigid cohomology theories that we constructed can be computed in terms of cohomology without compact support. Moreover, in this case, the Hyodo-Kato map for compactly supported cohomology satisfies the same properties as in the case without compact support. And similarly, as in the non-compactly supported case, our theory is compatible with the crystal inversions developed by Tsuchi and Yasuda-Yamada. Finally, if U is semi-stable but not necessarily proper, but we assume that it has a normal crossing compactification. Then the compactly supported cohomology of X is independent of the choice of the compactification. So it only depends on U, and this means we can define in this case the compactly supported cohomology of U. And the same is true for the other compactly supported rigid cohomology theories, and also for the Hyodo-Kato theory. As a last property, I want to mention that our Hyodo-Kato theory is a result of the comparison with Tsuchi's and Yamashita-Yasuda's result, satisfies Poincaré duality. To summarize our results, for a strictly semi-stable log scheme over V sharp, and a choice of uniformizer pi and a branch of the chaotic logarithm, we have a cohomology theory, R gamma HK with the rigid analytic Hyodo-Kato theory of S, together with a Frobenius and a monodromy operator, and a Hyodo-Kato morphism, which is in fact independent of the choice of pi. It allows for a theory of coefficients. Which are particularly nice for unipotent coefficients. And moreover, if X has a normal crossing compactification, we also have a theory with compact support. which satisfies the same properties as the one without compact support. And both of them together satisfy Poincaré duality.